9:42. Let's get started. Hello everyone. I hope you all had a good holiday yesterday, good day off. I definitely enjoyed not having to wake up to teach this class in the morning. Um, I hope you enjoyed not having to wake up to attend. Quick reminders, uh, I do not hate you. I just don't like waking up early. Um, Quick reminder, the problem set is due Sunday. I realize I haven't made a grade scope submission for that yet. I am going to make that right after class today. I'm also going to post solutions to the first problem set. We are currently in the middle of grading the second one, so hopefully that'll be released in the next few days. Exam is 5 days from today, so that is next Wednesday, July 10th. I've had a number of people already reach out to me to reschedule it. Hopefully, if you needed to reschedule it, you have already talked to me about doing so. But if not, please get that done as soon as possible. I will send out an email to everyone who has the exam rescheduled for not class time, just to make sure that that you know, or that we all know, to make sure that I'm aware of who's taking it when. The syllabus for the exam, I'll go over like what content will be covered on it, and I'll release a practice exam from I think this will probably be like spring 2020 or something like that. So you can sort of look over that. I think the first lecture slides described the list of topics that would be covered. So you can also take a look at that, but we'll talk about it. I think that's all the like course logistics stuff that I have. Oh, the second programming assignment is up, right? I know people are already working on that. We will hopefully talk about content related to that today. Problem set 3 is due on Sunday. So July 7th by midnight. And again, if you have your late days, feel free to use them. But yeah, any questions or clarifications about course things before we jump into content? All right. Okay, so I will create a whiteboard. All right. Can everyone see my scribbles? Okay. So last time we talked about binary search trees, right? In particular, we talked about first of all, finding an element from a binary search tree, right? The example, the sort of canonical example that I was using was 5, 3, 1, 4, and then 6, and I think there's an 8 here or something, right? And I'll put arrows. Right. So last time we talked about search, which is just a basic tree traversal, right? If I know the key that I'm looking up, if I found the key at the root, then I'm done. Otherwise, if the key is less than the root, I recurse to the left. Otherwise, I recurse to the right. And I keep going. If the root is null, then I know the tree is empty, and therefore the key can't be contained. And therefore, the tree doesn't contain the key that I'm looking for. right? So I can sort of write a recursive search procedure. We talked about insert, right? Which looks very similar to search, except if the key I'm looking for already exists in the tree, if the key I'm looking for is at the root, or the key that I'm trying to insert is at the root, I either overwrite it or I don't do anything, or I continue inserting it depending on what I want to do with duplicate keys. Otherwise, I decide whether I need to insert on the left subtree or the right subtree, and I recurse. Once I get to something that looks like null, I replace that null with a new node, a new leaf node that contains my new inserted key, right? And then finally, we had remove. This one, if you remember, was a little bit more complicated because we had to deal with like uh, almost like rebuilding a binary tree when we remove something, right? So if we, for example, if we were removing a leaf node, that's perfectly fine, right? There's nothing really to do. We just replace this with null. On the other hand, if we're removing something like the 6 here, it has exactly one child. So all we really need to do is promote the 8, right? And that becomes a perfectly fine binary tree. If we were removing the 3, that becomes a little bit more complicated. So if you remember, we actually, maybe it's easier if I talk about it as removing this 5, right? Because the only thing we're ever worried about is removing the root node because we're doing this recursively. So if we're removing the 5 and we've got like a non-trivial left subtree and a non-trivial right subtree, if you remember, we had to do this procedure of like figuring out what the new root needs to be, which is either go to the left and then keep going right as much as you can and get to the 4, or go to the right and then keep going left as much as you can and get to the 6, right? So we pick either the immediate predecessor or the immediate successor of our current root, of the root that we're removing, and call that our new root. So we create a new node. So let's say we pick the immediate predecessor. So we create a new node, call it 4. And then we make sure to go through and delete the original 4, right? And so this gives us another perfectly valid binary tree. So here there was 3 cases, right? But that's fine, right? We can quite easily we can do our recursive procedure to figure out where the node is that we want to remove if it exists, and then check to see which of the 3 cases were in and then handle it appropriately. And then we wrote some code to that effect as well. Okay, so that was the 3 operations that we talked about on binary trees. Now, I guess first of all, are there questions about that? Is there anything that people want me to go over on that part of the content before we move on? So I want to talk about balancing stuff today, but the balancing stuff only makes sense if you know how the insertion and deletion work. Cool. All right, let's get into it. Okay. So last time we also talked about time complexities, right? So insert, or let's just look at the complexity of like search, right? This was big theta of D, where D is the depth of the tree, right? Now ideally, we want D to look like log of n, right? If our tree is very nice and balanced, but D could be as bad as n if the tree is sort of this degenerate right? If I have like 8, 6, 5, 4, all of this down here, and then these are just null. This is in fact a binary tree, but it has a depth that looks like O of n, or I guess theta of n. right? So any kind of search over this tree is not going to give us the logarithmic complexity that we really want. It's going to be just as bad as searching through a linked list because morally, this thing is really just a linked list, right? Um, so uh, the thing that we use to sort of deal with that, to like make sure that that we don't accidentally find ourselves in this situation is this idea of like self-balancing binary trees. So self-balancing binary trees. Okay. There's two uh the particular kind of tree that we're going to talk about is the AVL tree, which we'll talk about today. In fact, right now, there's another thing called a red-black tree, which is similar to the AVL tree, but it's kind of like an optimization on top of that. We're not going to cover red-black trees in class, but I do encourage you to read about them because they're kind of cool. So I guess without further ado, let's get into talking about AVL trees. Hold my notes. Okay, so first of all, AVL stands for the last names of the people who invented them. So this is Adelson, Velsky, and Landis. If you're a cryptographer, you might recognize Adelson as the A in RSA. But that's neither here nor there. Anyway, the idea of AVL trees is we modify the insertion and deletion procedures to kind of maintain a balance, right? So if you think about like recursively, an empty tree is balanced, right? If I haven't inserted anything, it's already balanced. And then if after every single insert or every single remove, I make sure to rebalance the tree, then I can make sure that my tree always remains balanced. And I don't ever have to worry about this sort of degenerate linked list situation ever happening. So to do that, we're going to define, we're going to, I guess, start by augmenting our node data structure. So if you remember, we had like struct node, and this had an int value. I mean, it could be whatever. And then we had left and right pointers, right? We're also going to add an int for the balance. Okay. And the balance of a node is going to be defined as follows. So the balance of a node is going to be the height or the depth, or I guess I want to say height, of its right child minus the height of its left child, right? So if we look at an example, right? Here's a tree. The balance of the leaf nodes is obviously 0, right? Because their children are both null. The balance of this node here is going to be 0 because its left and right children are both have the same height. Oh, sorry, this is not a leaf node. Okay. Anyone want to tell me what the balance of this node is? Maybe shout it out or put it in chat. I see a -1. Any other ideas? I see a -2. Okay. We seem to be split on that. It is in fact -2, right? Because the right side, there's nothing here, so that's a 0, right? And then on the left side, I've got something of depth 2, right? I've got 1 and 2 here. So 0 minus 2 is -2, right? And then similarly, what is the balance of the root node? Any thoughts? I see a 0. Any other ideas? Right, what's the, I see a 2. Yeah, so I see a 0, a 2, and a -2. Okay, those are all the options. So it turns out if I look at the left side, right, there's a something of height 1. If I look at the right side, there's something of height 1, 2, 3, right? So 3 minus 1 is 2. So this is going to have a balance of 2, right? So you can kind of recursively compute this. Yeah. Anyway, does computing the or does this like definition of the balance of a node make sense? The height, so I'll say the height we can define recursively as maybe like or maybe I don't want to write code for it, but the height of null is 0, and the height of a tree is the max is 1 more than the maximum of the height of its children, right? So maybe I'll just say like height of t equals 1 plus max height t dot left. Yeah, right. So this node has a height of 1. This node has a height of 1. This has a height of 2. This has a height of 3. This has a height of 1. This has a height of 2. Right. And so when I compute the balance of the root node, I look at the height of 3 and the height of 1, and I do 3 minus 1. Height is like depth, but height is like depth. Yeah. It turns out um, if you're off by 1, like if you think of the arrows instead of the nodes, you mostly get the same balance just because like you'll get the same balance in most places just because like the ones cancel out. You thought depth was counted from the root? Yeah, so like the depth the depth of a node is like the length of the path from the root. The height is like the bottom up. So the height of maybe you want to say like the height of a tree is like 1 more than the depth of the 1 more than the maximum depth, right? Because we count the root as 1. How do you find the bottom of the tree? You mean like a leaf node? Like the bottom of the tree is just any node that doesn't have children, or like where both the children are null, is a leaf, and it's sort of at the bottom. If you want to find are you asking about like pseudocode for an algorithm that computes the maximum height? You literally you do this, right? You recurse on the left, you recurse on the right, you get the things, you take the maximum and you add one, you return that up. And then if you've got something that's null, you just return 0. Right? Any other questions? All right. So yeah, okay. So this is the definition of like the balance of the node. We can augment this and maybe say another definition. The tree, I guess I'll say like a binary tree, is balanced if every node has a balance of -1, 0, or 1, right? So in particular, if we look at this tree that we drew here, this tree is not balanced because we've got a node with a balance of -2 and another node with a balance of 2, right? If we look at our favorite tree from before, which was like 5, 3, 1, 4, 6, 8. Actually, maybe it's worth computing the balance of the nodes here, right? So what's maybe just shout this out in chat. What's the balance of the node at 1? Zero. Yep. What about at 4? I'm going to do a post-order traversal of this tree. Someone else this time. Yes, thank you. It happens to also be 0. Anyone want to tell me what the balance of the node at 3 is? Also 0. What about 8? Also 0. What about 6? 6 is 1. Yep. What about 5? 0. Perfect. Okay. So if we look at every node here, it either has a balance of 0 or 1. Therefore, this tree is balanced. Right? And that kind of fits with our intuitions, right? Like this looks balanced. If it was -1, it would still be balanced, right? So if instead of an 8, this was like a 5.5 or something, and we didn't have this 8 here, then the balance here would be -1, and that would still be balanced, right? The reason we have to allow -1s and 1s is because obviously you get you can have trees like this where it's not possible to have every node have a balance of 0. But anytime you have something with a balance of 2 or -2, it's possible to fix that. So we don't have to go any further, right? And in fact, that's exactly what we're going to talk about here. So hopefully the idea of like the balance of a node or like balanced trees or whatever, hopefully this kind of makes sense. I don't think it's particularly deep, except just like as a definition. So maybe we can talk about an actual balancing procedure, right? So for an AVL tree, keep writing AL. I don't know why. AVL insert, right? So if we have a tree and we have a new value that we want to, or I guess I'll call it a key that we want to insert, right? We start by doing a regular insert on the tree and the key, and then we call rebalance on the tree, right? So the sort of interesting thing really happens in this, or like the crux of the AVL tree is this rebalancing procedure, and the fact that we can do this efficiently. And just for the sake of completeness, I'll also write like AVL remove. Is just going to be remove. And then we're going to do the exact same rebalance. Of course, the rebalancing might look different because we've removed a node instead of inserting a node. But it's going to be the same, right? And in particular, like all of the complexities of like is the node that I'm removing at like a leaf? Does it have one child? Does it have two children? What do I do with that? All of that gets handled first, and then we think about rebalancing, right? So we do all of that. We compute the new balances of the tree, and then we worry about rebalancing. Now, the reason that this is actually okay, or the reason that like asymptotically the complexity of this is fine, is it turns out if I'm it turns out that we can rebalance a tree without like rebuilding the tree from scratch, right? So obviously, like one way to balance a tree is to just read off all of the nodes and then sort of insert them into a new tree in a more balanced fashion. But that's big O of n. That's a big theta of n. And so that would mean that our insertion and removal procedures are also linear time, and that kind of like defeats the purpose of using a tree if everything we do with it is linear time. Okay, so let's look at an example of insert. Let's look at rebalancing in the context of an example first. And then we'll break it down further because it ends up being like a big case statement. So maybe it's easier to start with a picture. I'm going to redraw 5, 3, 1, 4, 6, 8, right? Let's say I want to insert the node, or I want to insert the key 10, right? First of all, can anyone tell me where 10 should go in this tree? Like if I run my insertion procedure, where is 10 going to end up? To the right of 8. Perfect. Thank you. Great. So I put a 10 there. Now insert is fine, right? Like insert is perfectly fine with this. However, as an AVL tree, if we now recompute the balances of every node, right? We get zeros here because we haven't changed anything on the 3, 1, 4 side, right? Not balanced because 6 now has a balance of 2. That's right. And 8 has a balance of 1, 10 has a balance of 0, and 5 has a balance of 1, right? So yeah, there's this problem now of 6 having a balance that isn't -1, 0, or 1. Is recomputing the balance of every node, presumably O of n, something that we would do? So as you'll see, we don't actually have to recompute the balance of every node, right? The only things that we have to, like the only heights that change are the ones on the path from the new node to the root, right? So anything that's off that path, like for example, if we had like a 5.5 here, and this had like all sorts of crazy stuff going on, right? We wouldn't have to touch the balance of this. We wouldn't have to recompute anything here because this shouldn't like this tree shouldn't be affected by something going on over here. And so recomputing the balance is actually just, we look at the node that we've inserted, and then we just like recurse up to its parent and its parent and its parent and update their balances. And so that ends up being theta of log n. Assuming, of course, that the tree was balanced to begin with, which, if we're doing this inductively, we make sure that it stays balanced at every step, and so we're allowed to assume that it's balanced before we insert, as long as we rebalance it after insertion. That's a good question. Does that make sense? Like, does it make sense why recomputing the balance is not terrible? Okay, awesome. Okay, so now that we've got this, right, we have this problematic node, which is 6 with a balance of 2, right? We need to fix this somehow. The issue is really that it's like 6, 8, 10, right? There's just a long chain with nothing else really going on, and there needs to be a better way to encode this, right? And so it turns out, if you were to just look at this sort of subtree, this 6, 8, 10 subtree, what should the root be? I mean, obviously the root of this tree currently is 6, right? But calling the root 6 leads to something very unbalanced, and we don't want that. So what's a better choice for the root? 8, yeah. So if I make 8 the root, then 6 goes on the left and 10 goes on the right. Yep. And the name that we give to this operation of going from 6, 8, 10 to 8, 6, 10, this is a rotate, right? So I'm going to call this, what is that, counterclockwise? I'm just going to call it rotate to the left. Yeah, or like counterclockwise rotate, right? So yeah, you can think of it as like taking this and sort of rotating it to the left, and so we end up with something that looks like this, right? Similarly, of course, we could rotate to the right. Right, if we had something like 6, 5, 4, then a better choice for root would be the 5. And so we'd make this 5, 4, and 6. And this would be like rotating it to the right, or like a clockwise rotate. Right. But the point here is we can sort of look at the 6, notice that it has a balance of 2. And that tells us that the right subtree is a lot heavier than the left subtree, which means we want to shift things to the left. So we're going to rotate it to the left, right? And so in particular, after applying this rotation, the new like rebalanced tree that we end up with is, or the new tree after rotating is the 5 stays the same, the 3, the 1, and the 4 stay the same, right? We didn't have to touch these. And now I replace the 6 with my rebalanced 8, 6, 10, right? And if I compute the new balances after performing this rotation, of course, these all stay the same. I can no longer count on the 5 to stay the same because I've changed one of its subtrees, but the 6 is now 0, the 10 is 0, the 8 is 0, and the 5 happens to also be 0, right? And so we've gone from this unbalanced tree to a balanced tree. Right. So maybe to make this more concrete, to make this more concrete, the way we've done this is like we look at where we've inserted a new node, right? So we've inserted at 10, or we've inserted this 10 here, right? And we kind of move up. so we recurse up to find the root. So go from new node to root, find the first unbalanced node, and rotate it, right? So we start at the 10. We traverse up to the 8 and then up to the 6. And once we hit the 6, we find that it has a balance of 2. Or we start at the 10, right? We know its balance is 0. We move up to the 8. We compute its balance. It's fine. It's 1. We move up to the 6. We compute its balance. Now it's 2, which is bad. And so now we know that we have to balance at the 6, right? And it turns out there are sort of 4 separate cases to check. So how would this rotate work if there was something to the left of 8? Yeah, okay. So maybe I can before I describe the cases, maybe I can be more specific about the rotate. So in general, rotate is going to look like I'm going to call these nodes like A, B, and C, right? So we've got A, B, and C, and I've got like a T1, T2, I guess with like T3 and T4, right? The T's are just arbitrary trees. They're not necessarily single nodes. They might be null. They might be something very complicated. But if I rotate this to the left, B becomes my new root. A goes to the left, and C goes to the right. A gets T1 and T2. C keeps T3 and T4, right? And we know this is fine. Like the only thing that's really moving is the fact that T2 has gone from the left child of B to being the right child of A. But we know this is fine because in particular, what we know about T2 is that it's on the right side of, like it's currently on the right side of A, which means that T2 is greater than or equal to A. And it's on the left side of B, which means that it's less than or equal to B. But if we put it here, like it's to the left of B still. So we know it's like, this is still fine because it's less than or equal to B. And it's on the right side of A, which is fine because we know it's greater than or equal to A, right? So we've sort of moved the left subtree of B to be the right subtree of A in doing this rotation. But we know that that's fine because it was a binary tree to begin with, and so it remains a binary tree afterwards, right? How could we be sure about it being bigger than A? Oh, because it's on the right. I mean, a binary tree, remember, is defined by the fact that every node to the right of the root is greater or equal to the root, and every node to the left of the root is less than or equal to the root, right? Oh, was there another question? Yeah, every node, right? So in particular, we also know that T3 and T4 are at least as big as A, right? Well, that doesn't matter because they're not moving, right? C is to the right of A, C stays to the right of A. Or in particular, C is to the right of B and C stays to the right of B, right? Cool. That's a good question. Does anyone else, or does that make sense to everyone, or does anyone have other questions about the rotate before we go further? Okay. So the okay, yeah. Let's look at the sort of 4 cases for rotation. I'm going to describe 2 of these cases. The other 2 are going to be symmetric on the other side. So I'm only going to talk about rotating to the left. You can stick negative signs in all the appropriate places and call it rotate to the right if you want. like swap the left and the right. I mean, the algorithm is the same. The vibes are the same. You just kind of pick which side you're gonna go on based on whether it's a positive balance or a negative balance, right? So maybe let's go back to here, right? So we go from the new node to towards the root. We find the first unbalanced node that needs to be fixed, and if it's let's assume that the first unbalanced node, actually maybe I want to write over here. Space management is so hard. Okay, so let's assume without loss of generality that the first unbalanced node has a balance of +2, right? If instead it was a balance of -2, we would do the same thing, just replace right with left, replace clockwise with counterclockwise, or counterclockwise with clockwise, and so on, right? You do the same thing, just flipped, right? Mirror image. So yeah. Why is it enough to assume that its balance is +2? Like, why do we not have to think about the case where its balance is +3? That is going to be your attendance poll, right? Let me write that down. Attendance poll. Why do we not need to handle a balance of +3? Okay. So let's assume without loss of generality that the first unbalanced node has a balance of +2. I'm going to write this down again. So we've got A, B, C, T1, T2. And I'm not gonna write any subtrees under C because right, we know that in the rotation process they're not changing. Okay, so if the balance of A is +2, that means the height of B, like the height of B minus the height of T1 equals 2, right? Or maybe I want to say like the height of B equals the height of T1 plus 2. Now, if I perform my rotation, I get B as the new root. I get A on the left, T1, T2, and I get C over here, right? What's the new balance of A? Well, the thing is, I don't know what the height of T2 is, right? But it can't be more than 1 less than the height of B, right? So the max possible height of T2 is actually maybe I want to say like the height of T2 is less than or equal to the height of B minus 1, right? Because if it was any more than that, if it was equal to the height of B, then the height of B would be 1 more, right? So the height of B is either dominated by T2 or C. The maximum possible height of T2 is the one where it dominates the height of B, and so it's this, right? Which is in particular less than or equal to the height of T1 plus 1, right? And we can also say that the height of T1, because the balance of A is 2, right? T1 can't be can't be more than like can't be bigger than T2, right? In fact, can't even be as big as T2, right? So we know that the height of T1 is less than or equal to the height of T2. Because if the height of T1 was equal to the height of T2, then these two would be equal, which means B would be one more, which means it would be balanced, because this would have a balance of one, right? So we can sort of actually, I don't think that's what I want to say. I think first I want to make an assumption that B is either 1, 0, or -1, right? If B is 0, then we know T2 and C are the same, which then means, of course, that T1 has to be less than or equal to T2. If B is -1, that's no longer the case. T1 can be one more. But sort of either way, like we see that after performing this rotation, A has to be balanced, right? The question is B balanced after doing this rotate? And whether B is balanced or not depends on what the original balance of B was, which in particular depends on like the relative weights of T2 and C, because if we know that T2 is dominating the height of A, then if C was dominating the height of B, then it'll be balanced. If T2 was dominating the height of B, then now B is unbalanced, right? Because if T2 dominates the height of B, that means the height of T2 is greater than the height of C, which means that if T2 was dominating, if T2 was dominating, then you'd rotate right is the question. The answer is right now we're trying to rotate. I mean, the first rotate that we do is trying to fix A, right? So in the case of A, we already know that B is dominating T1, right? So we have to rotate to the left. The question is, after rotating to the left, is this new tree perfectly balanced? Like, is this fine, right? And the answer is if T2 was dominating the balance of B, or if T2 was dominating the height of B, that means the height of T2 is greater than the height of C, which means that after this rotation, the height of B is going to be the height of T2 plus 1, right? So the height of B is going to be greater than the height of C plus 1, which in particular means that like T2 was already too big. We're adding 1 to it, so now B is unbalanced, right? In particular, this means that if B starts at -1, right? So if B starts at 1, then C is bigger, which means that when we push T2 down by 1, it becomes balanced, right? So B -1 goes to 0. B at right? If T2 was no, B1 goes to 0, because if C is bigger, then we rotate to the left, B goes to 0. B0 goes to -1, right? For sort of the same reason. But now if B was at -1, it becomes -2, and that's bad, right? So we have to rotate A to the left anyways, because it was at 2. But if B was also -1, then it becomes a -2, so now we have to rotate B to the right. Right? Well, if B was -1, that means T2 was too big. The 4 cases depend on the balance of A and B, essentially. Yeah. Right. So the 4 cases are maybe I can just write this out. You go until you find A, B, C, where A is the first unbalanced node. And B is the child in the direction of insertion, right? If we inserted on the, like, we don't care about the left child of A because if we inserted on the right, we don't care about the left child of A because nothing changed on that side, right? So if A equals 2 and B is greater than or equal to 0, rotate left at A. If A equals 2 and B is less than 0, rotate left at A and then rotate right at B. And then if A equals -2, it's the same thing, but the other way around. So you rotate right, or you rotate right and then rotate left. Right. So that's how you balance. That's how you rebalance after an insertion. And the thing is, like, changing once you've sort of changed A, right? The where's the, here we go. Yeah. So once you've changed A, this might affect, like, obviously the height of the height of B is now different, right? Because the root is now B. And so the height of this node is now different, which means that you now have to propagate that balance information upwards, right? So balancing this tree might cause its parent to become unbalanced because its parent might have been at like 1 or -1, and switching that balance might push it over the edge into 2 or -2. And so then we have to sort of recursively balance the parent and then balance the parent and then balance the parent, right? So in the worst case, this will require us to, like, the worst case is sort of like where we've got a bunch of 1s down the line, right? And so inserting something turns this into a 2, balancing it pushes the 2 up, balancing it pushes the 2 up, and so on. And so the worst case complexity of this is theta of log n rebalancing. Right. And again, the reason this is log n and not O of n is we don't actually have to balance every single node, because we know that any node that's not on the path from the inserted node up to the root is not going to be affected, right? Because we're not changing that part of the subtree at all. So we don't have to, like, rebalance it, right? Its height isn't going to change, its balance isn't going to change. So the most work we'll ever have to do is on the path from the new node up to the root. And if our binary tree started as balanced, then the length of that path is going to be at most log n, right? And so the overall complexity of insertion is the log n traversal to insert. Could I say the last bit again? Yeah. So the idea is if I've got a tree with like a bunch of stuff going on all over the place, right? And I insert something here, say insert something right there, right? I have to propagate the balanced stuff up, right? So maybe this node becomes unbalanced, so I have to fix that, which makes this node unbalanced, so I have to fix that, which makes this node unbalanced, so I have to fix that, right? And I have to sort of keep going up until I hit the root. And once the root is balanced, then, like, balancing it, there's nothing above it to dirty, right? But the time complexity of this, like, recursive balancing procedure is only ever going to be theta of log n. Because if this is where I've inserted my new node, I'm never going to have to worry about the balance of this subtree on the left, right? Because its height isn't changing. None of its children have their height changing. And so none of its children's balances are being updated, which means if it was balanced to begin with, it's going to stay balanced. Exactly. It remains untouched, right? So the most work I ever have to do is rebalancing every node on the path from the new inserted node up to the root. And because my tree was balanced to begin with, the length of that path is at most log of n. Right? So the rebalancing procedure is, in the worst case, theta of log of n. Right? Or I guess you can say it's always O of log n. Right? Bounded from above by log n. Right? So in particular, the AVL tree insert is a log n insert plus a log n rebalanced. So the overall complexity is still just log n. For removal, it's exactly the same. right? We do all of our removal stuff. We figure out where we've removed the node from. The like removal always removes something from the leaf, right? Because even if the thing we didn't, even if the node we removed had two children, we end up like moving one of the leaves up to be the new root, and then we just like delete like the actual like change in the shape of the tree happens from deleting that leaf. So we sort of do the same thing, except now we start from the leaf that we deleted and then go all the way up to the root and find the first unbalanced node and then look at these four cases and do exactly the same thing, right? Does that make sense? Any questions? Why does it always start from a leaf? What if the node we delete isn't a leaf? Yeah, so if you remember, our removal procedure is like um right, if I've got, I mean, maybe I've got some other stuff going on above this 5, but if I've got like the 5, 3, 1, 4, 6, 8, right? This is my favorite tree. If I delete the 5, what that really amounts to is moving the 4 up, right? And then deleting the 4. Right? So in terms of like the values might change, right? But I don't care about like the values of the keys in the tree. I just care about the shape when I'm trying to rebalance it. So the only node that I've removed is this leaf. Good question. Any other questions? Okay. In the last minute or so, I want to maybe start talking about KD trees just because those are probably going to be useful for the programming assignment. But we'll cover those in more detail on Monday's lecture. The general idea of KD trees is like, I mean, think about this in one dimension. It's really just a binary tree, right? If I've got a line with a bunch of points on it, right? This is like, you know, maybe my points are 1, 3, 4, 5, 6, 8, right? 1, 3, 4, 5, 6, 8. Um, an easy, like the easiest thing I can do is just put all of these numbers into an array or like a linked list or something. And then of course, searching over this is like big O of n. But the idea of a binary tree is I can do a lot better by like putting points that are close together on the tree. And so I can start by like splitting, right? Maybe I picked 5, right? So I split at 5. How do you determine collision once you split the tree by axis? That's a good question. I'll get to that in hopefully a second, right? So if I split the tree at 5, I've got some points on the left, some points on the right. I can recursively split at 3, recursively split at 6, right? And I can just keep like subdividing this number line down the middle a bunch of times until I get until all of my points fit on a tree, right? The very high level idea of a KD tree is similar. So now instead of on a line, they're in some like d-dimensional space. So I'm going to draw 2 dimensions, but you could imagine this being a cube. You can imagine this being like a hypersphere or whatever, right? And I've got a bunch of points sort of all over the place, right? So now I have to pick the dimension I want to slice along. So I can make a vertical slice or a horizontal slice, and I have to pick where I want to slice it. But I pick a slice, and this gives me a tree where the root represents the whole space and the 2 children represent like the top and the bottom, right? I can then maybe slice the bottom into a left and a right. And then maybe I want to slice the right into a left and a right. Maybe I want to slice the left into a top and a bottom, right? And so I get this tree. And I can keep subdividing until I get a single node or a single point in each node, or I can subdivide down to like a certain size. That's sort of up to me. In terms of collisions, the thing you want to think about is like if I've got a circle here and I like a circle of a certain radius, which nodes does it intersect with, right? If it doesn't intersect with this entire box over here, then there's no point in checking any of these points. So the only points I have to check are the points in the nodes of the tree that the circle, that the radius intersects with. So things to think about. These aren't any concrete algorithms. There's a lot of like design decisions to make here. These are called KD trees, if you want to read more about these. We're going to talk more about these on Monday. We're also going to talk about something called quad trees, if there's time, or maybe oct trees, right? And other spatial indexing things. But I figured I would say just enough to maybe give you some ideas for the problem set. Anyway, I've now gone a few minutes over, so I apologize. Any last minute questions? If not, you are free to go and enjoy your weekend. Be free. Ask a couple questions about the PA. Yes, absolutely. I'm going to pause the recording. The attendance, oh yeah, maybe before I pause the recording, the attendance poll is this.